I will start by making short introduction to the three speakers. Our first speaker is going to be Mr. Ulrich Kabler. Ulrich is based on Lustenau, Austria. He is heading the Obrist Group sales activities worldwide since June 2024 as a Chief Sales Officer. Ulrich holds a master's degree in communication engineering from the University of Ulm and an international marketing and export business degree, MBA, from the University of Applied Sciences in Rüttingen. He has more than 30 years of experience in high-tech marketing and sales in the telecommunication industry, working for companies such as Siemens, Infineon, Nortel, DASA, MD, Satcom, SES, and DCT Delta. The second speaker is Dr. Johannes Pock. Johannes joined Obrist Group 1.5 years ago as a CTO. Johannes holds a PhD in inorganic chemistry, photovoltaic, water splitting from University LFU Innsbruck. Before Obrist, he worked 4 years as a processing technology in electroplating at Collini Group in Austria and Mexico. And our third and last speaker is Mr. Chris Mustburger. Chris joined Obrist in 2020 and works under founder and CEO Frank Obrist as his right-hand man. With an academic background in mathematics, he likes to look at the complex picture of today's energy landscape in a holistic manner. Chris has experience in technology, IP, economics, calculation, and support Obrist sales and marketing activities as well, bridging the gap between the technology activities of Obrist and the real world. So I'm welcoming now the first speaker, Ulrich. You are welcome to start, please.
Thank you, Shmuel, for making the introduction. We might wait for another few seconds to have all participants joining in. We had, unfortunately, that small technical problem with Zoom. So luckily, we are not in the IT type of business, but we are in real business, such as A-fuels and real technology. I'd like to introduce you to the Obrist Group, which is active in the market since more than 25 years. All our projects are a combination of leading-edge technology with a sustainable and renewable touch. So we could consider ourselves a technology enabler. So we're not producing anything, but we work in partnership with the big manufacturers that benefit from our very special engineering know-how to improve the efficiency of their systems and solutions, and at the same time, of course, to shorten the time to market, which is very crucial these days. Within Obrist, we have about 80% of the colleagues with an engineering background and degree. So all our research is fully concentrated on sustainable and emission-free and emission-reducing solutions. And overall, it led to more than 500 patents we hold in the company. Obrist Group consists out of 3 pillars. Let's start with the Obrist engineering. There we concentrate on climate compressors, and that's basically our origin of the company. But it does not stop with climate compressors. It goes over to pumps for liquid hydrogen that have to work at minus 250 degrees Celsius, and also very special air compressors. So the origin here is again from the automotive industry, but it more and more goes into stationary applications. All those products are related to environmentally friendly coolants. And of course, our customers are then typically the tier 1s or the OEM manufacturers. In an Obrist powertrain, excuse me, we have developed a complete powertrain concept to allow an OEM to develop, coming from a battery electrical vehicle, to develop that or to extend that into a serial hybrid vehicle that runs on CO2 neutral fuel. And we think that this is the only possibility to really have a mass implementation of CO2 neutral vehicle fleets, also in countries and areas where you do not have an electrical charging infrastructure.
Kom her. Jeg kan kjøre rundt hvis vi skal be.
Ulrich, you can continue.
Okay, my mic was muted, sorry. So Obrist Technologies would be the third pillar, where we fully concentrate on technologies to produce green methanol at a very cost-effective area. And by this, we can produce CO2 neutral fuel, but even we could produce CO2 negative fuel. Next slide. I think we all agree and know that the root cause for global warming is the concentration level of CO2 in the atmosphere. On the right-hand diagram, you can see the development of the temperature deviation from a medium over the last 50 years. And this is clearly linked to the left-hand side diagram, where you can see the concentration of CO2 in the atmosphere. There are, of course, numerous activities from the UN and, of course, all over the world in different countries to reduce or to get to a CO2 neutral level by 2050. And this will be an extreme effort for everybody around the world. We as Obrist think that this is actually not enough and we have to go further. And we have even to reduce the concentration of CO2 in the atmosphere by 20 or after 2050. The following technology, which is direct air capture, which is all about that webinar, is one of the building blocks where we think we can reach that ambitious goal. And I'm happy to hand over to Chris Meusberger to explain you how we want to do that.
Thank you very much, Shmuel and Ulrich, and also hello from my side. Before I start, just a quick organizational reminder to please keep your microphone muted during the presentation. We will have a question and answer panel after the presentation, but in the meantime, to avoid any intermittencies. Thank you. Yeah, I want to start today with a very basic overview on what exactly direct air capture is and how it works. In essence, direct air capture is exactly what it says, capturing CO2 directly from the air and then providing it in concentrated form for subsequent processes, whether that is for storage, conversion, chemical synthesis. On the one hand, that sounds fantastic, tackling the problem of excess CO2 in the atmosphere at its very core. On the other hand, it is definitely not easy to do because the concentration of CO2 in the air, even though it is too high, is still very low at around 420 parts per million, or just over 0.04%. To capture something that scarce and provide it in essentially pure form is a substantial technological challenge. To solve this challenge, there are, of course, multiple approaches, with each and every one of them having their own strengths and weaknesses. The most common classifications are through the type of process being used, as well as releasing the CO2, how the CO2 is released from the process. One can differentiate, for example, between chemisorption and physisorption processes, or adsorption and absorption. Process type also sometimes refers to the type of sorption material being used, for example, a liquid material versus a solid one. With regards to the release of CO2, one can release this from the used sorbent material through different ways as well, depending on the process. For example, through heating up the sorbent material, which would be called a temperature swing, or creating a vacuum around the sorbent, which is equivalently called a pressure swing. Finally, other aspects such as the application of the CO2 product, so whether the CO2 is used in a product or stored subsequently, further the condition of the CO2, especially regarding purity and or water content, and then finally also the type of energy being used, so thermal or electrical energy. All of these are also sometimes mentioned to differentiate between various direct air capture technologies. Now, I do want to talk a little bit about several criteria that can and also should be used to assess technologies and their viability, potentially for different use cases. Before I go into further detail here, I want to point out one very important thing. Direct air capture takes up energy, and not that little. Even though the theoretical value for the energy that is needed is quite low at around 140 kilowatt hours per ton of captured CO2, the reality is that most processes in direct air capture lie way above that measure, with 2,000 to 3,000 kilowatt hours per ton being quite typical, sometimes even more than that. Because direct air capture typically needs such a high amount of energy, it is important to consider the most cost-effective possible energy sources in the world that are also green and renewable, of course. Luckily, the cheapest primary energy source in the world is photovoltaics, specifically deployed in the solar belt of the Earth. And in order to be able to leverage this energy source, the DAC technology has to hold up in the unique conditions presented by those regions. In that context, it makes a lot of sense that our criteria for good direct air capture are very much focused around that condition. Things like water retention, stability towards hot ambient conditions, and so on become very important in the context of operating in the solar belt, where the air is dry and hot. Of course, that is not all. We believe that a DAC technology that needs to be deployed on a gigaton scale needs to tick other boxes as well, such as, of course, general affordability and being able to be endlessly scalable and deployable. These are the criteria we had in mind when looking for and developing a solution. And what we came up with is a technology that we believe meets all of them. With all that in mind, I want to now hand over to my colleague Johannes to tell you about our proprietary Obrist DAC technology.
Okay, also hello everybody from my side, and thank you for joining. And thank you, Chris, for the nice overview. On this slide, you see a short overview of our own DAC process, and in the next slide, we'll go into a little bit more detail. First, as a quick reminder, there will be no DAC process that suits everyone, meaning there are DAC processes that are better suited for direct air capture storage. There are DAC processes that are better suited for direct air capture utilization. There are DAC processes that are better suited for the colder climate or for the warmer climate. So there is no one fits all solution, obviously. So our process, the goal from our process was that it's suitable for direct air capture utilization. More specific, the main purpose is to use the CO2 to synthesize methanol. This means we need a certain purity of the CO2 mainly. And also one of our goals was that the process, as Chris has already mentioned, solar energy is at the moment the cheapest renewable energy that is around, that the process works in the solar belt where there can be rather hot and dry conditions. So on this slide, you can see basically what our process is about. In the first step, air, more specifically the CO2 from the air, is brought into contact with a sodium hydroxide solution. There is similar processes that work quite similar in this first step. Maybe to tell you a bit, sodium hydroxide is one of the 5 most produced industry chemicals in terms of quantity. So it's quite abundant and there will be no shortage, which is also very important to consider since we are tackling a gigaton problem. It's brought into contact with CO2, and this forms sodium carbonate. This was used in washing powder, so it's also nothing special. What's very unique here about this reaction is that the bond that is formed here is very strong. This means if the column height from the reactor is high enough, one could remove up to about 90% of CO2. And in the end, it's all about optimization. But here, what's maybe different from our competitors is that we will obtain the sodium carbonate in solid form, so we can separate it. Before I mentioned it's a very strong bond, so the reaction of sodium hydroxide with air is simple and fast, so to say, even though it's only 420 ppm in the air. But this also has a downside. If the bond is very strong and the reaction is very easy, the reaction, to turn the reaction around, meaning to release the CO2 again, is not that easy. In terms of energy, this would mean one would require about 1,600 degrees Celsius of heat energy to release the CO2 again. And these, of course, are not temperatures that we want to work with in terms of material, and also in terms of it's not economical. So what we did is we have an electrochemical conversion that is here. We convert the sodium carbonate to sodium bicarbonate. As you can see here, sodium bicarbonate is also part of baking powder. And this now has the nice thing that you can already release the CO2 at temperatures starting from 50 degrees. At the same time, in this process, the sodium hydroxide is recovered, even though there's a lot of sodium hydroxide, since the process has to be closed, and it has to be a cycle that no chemistry, no mass is lost in this cycle. And then in the end, via direct release by heat, we obtain the CO2. In the next slide, I want to talk about it in a bit more detail. It looks a bit complex at first, but let's go through it. This is basically the same slide as we had before in a bit more detail. So here on the left side, can be seen that the sodium hydroxide solution is circulated and brought in contact with the air. A solid is formed inside the tank. The solid has to be separated and can be collected outside, and is then brought into the second step. Here a bit more specific. This is an electrolysis cell here. And the most important, we have a very diverse audience here, so if it's too much detail, please apologize. This cell does basically three things. On the one hand, hydrogen is produced. On the other hand, the sodium hydroxide is recovered to brought back into the first step. And on the thirdly, the sodium carbonate is converted into sodium bicarbonate. What's the important takeaway here is that this process is quite similar to the chloralkali process. Why is this important? Because as you remember, sodium hydroxide is among the 5 most produced industry chemicals in the world, and this chemical is produced mainly via chloralkali process. And this also means this process is already sort of at a very, very high TRL and already available at large scale. So this is, by the way, an approach that many other DAC companies also take, that they look for processes that are already available on industry scale, try to modify them so they can suit the DAC process and then utilize them. because as you know from the first slide, this is very important because we simply do not have the time to do a lot of development and have to scale up DAC as fast as possible. In the last step, the sodium bicarbonate, which you can see the orange arrow is just brought into a heating reactor. And in this reaction, next to water and sodium carbonate, CO2 is formed. Here, the nice thing is as well also that we have temperatures of decomposition already starts at 50 degrees, and we have a very nice reaction speed at about 120 degrees, which is very different from these 1600 degrees. So to sum up, we have the first step where we have the capture process. We form sodium carbonate, which makes a very strong bond. In the second step, more or less, we invest a bit of electric energy into the system, but not all the energy is provided by electricity. So in the third step, we can use low-grade waste heat energy to finally release the CO2. So please, the next slide, Chris. Here to see a bit how it looks like. We built several prototypes. This is one prototype of the first stage of our process we made in Lindau in Germany at the Lake of Constance. It was under construction. This is our second prototype, and in this case, we wanted to show that in principle, one could use for this step at least very cheap materials to use it. We don't need high-tech tanks or whatsoever for this. Okay, and in the next slide, I want to talk about the energy consumption. As Chris already mentioned, we had a bit of a different approach in our process. We did not want to be the best in terms of energy per ton CO2 captured, but we were planning to be the best in energy cost. Also, in terms of energy cost per ton of CO2 captured, that can be used for methanol synthesis. So on the left side, you can see the energy, electric energy and thermal energy. The electric energy, keep in mind, the process is designed that it can be used and deployed in the solar belt of the Earth, where we can use very cheap renewable energy in terms of solar power. We have a lot of thermal energy that is needed, but this thermal energy is no high-grade heat. We need energy up to maybe 100, 150 degrees Celsius. And this is energy that can be, our temperatures that can be reached either via solar thermal power, or even better, if you have a methanol plant next to it, this can be covered by waste heat. And on the right-hand side, you can see these calculations in euros per ton of CO2. As you can see, the thermal energy we could more or less exclude, because we thought about the waste heat, the low-grade waste heat we can use in the process. However, without this waste heat, this number would be about 17, 18 euros per ton, so not that much more. And the biggest part would be the electrical energy that is used for the electrolysis part. Here again, with this 1 cent per kilowatt hour that is possible already in these regions, we could end up at very, very low costs. Okay, so these were the most important parts from my side. So Chris, I think I will hand over to you again.
Yes, thank you, Hannes, for this overview. I just want to give a quick word on what we actually want to do with direct air capture and our own direct air capture, and why we do things as we do them. Yeah, in short, we want to create an energy carrier, specifically methanol, produced in a climate positive way, which we call A-fuel. Direct air capture, of course, plays a crucial role, since with A-fuel, we do not only want to reach CO2 neutrality, but even CO2 negativity. So we actually want to take out more CO2 from the air than what is emitted from using the A-fuel. We do this by including an active carbon sink process into the mix. For this reason alone, it is vital to be able to effectively capture the CO2 not only from point sources, but directly from the atmosphere as well, and also in an affordable manner. The resulting methanol is the energy carrier that for us poses the ideal sweet spot between ease of production and ease of use. With it being liquid under standard conditions, it is easily transported using existing infrastructure, whether that is via pipelines, tanker ships, or fuel stations, and also used in a wide variety of applications that use fossil energy today. One quick word here, we believe that this energy carrier has applications that go way beyond our original industry of automotive, where we're coming from. Indeed, all forms of mobility can directly or indirectly be served by A-fuel, but also other major energy consumers of today, such as all kinds of industry, thermal power plants, residential users, could be supplied with A-fuel. Finally, of course, the chemical industry, which is the main consumer of methanol today, already provides a mature and existing market for the products. So, what exactly are our plans? Well, here you can see basically our end goal, which is the construction of so-called gigaplants in the solar belt for the large-scale industrial production of climate-positive A-fuel. These plants are designed to be energy autonomous and perfectly leverage the abundant solar energy in the sunbelt of the Earth. Of course, there are a few steps that are coming before that, with multiple intermediate projects underway that will be paving our way towards the gigaplants. We will give updates on these steps, on these next steps in due course. And so I hope you keep your eyes open for news on our coming activities. For now, this brings us to the end of the presentation. I want to say thank you very, very much for your attention. And
good. Yeah, I think we have covered quite a lot. Our questions show that you are obviously interested, and I mean, we are, of course, totally convinced that we have an extremely interesting technology on hand to really tackle that problem, which I introduced at the beginning. So I can only invite you, as I said, please get in contact with us if you have further questions, or of course, if you're interested in that technology to further progress it together with us. For us, it's always a partnership. And yes, thank you very much for your time, for your interest, and I wish you, and we wish you a good end of the working day, hopefully.